to Sean. In this video, we are going to find the radius of convergence of some power series. We will be using the ratio test to find the radius of convergence. So if you need a refresher on the ratio test, I made a video. I put the link to the video in the description below because I'll take some algebraic shortcuts through setting up the ratio test just to conserve time and space in this video. So the radius of convergence, there's a theorem. We have three different situations, three different possibilities when computing the radius of convergence. Okay, so as I said, we're going to use the ratio test. We're going to see what happens with the ratio test. If we run through the ratio test with our power series, and if our ratio test is a divergent, if it diverges, okay, then your radius of convergence will be 0, and your power series will only converge at its center. All right. So if you do, that's case number 1. Case number 2, if you use your ratio test and it converges for all values of x, if you have converging for all values of x, then you're going to have radius of convergence to be infinity. All right. And then your third condition here is you're going to have some positive number r where the series will converge if the absolute value of x minus the center is going to be less than r, and it's going to diverge if it's greater than r. So we're going to see each of these three cases here with these three examples. Okay, so let's start with our first example. We want to generate what the radius of convergence is by using our ratio test. So our ratio test, we're going to take the limit as n goes to infinity, and it's going to be absolute value. You take the a sub n plus 1, okay, over the a sub n. So we want to put the n plus 1th term in the numerator and then the nth term in the denominator in absolute value signs, okay? So we want to change the n's to n plus 1 for the numerator. So you have 5x to the n plus 1 over, and then you have down here 2 to the n plus 1 factorial. There's your n plus 1 term. Put it over your nth term, which is essentially what this is. So 5x to the n over 2n factorial. Okay. So to generate your using the ratio test, we're going to put the a sub n plus 1 term over the a sub n. As you can see, it generates a complex fraction. So we want to go ahead and simplify the complex fraction. We're going to take the numerator and we're going to multiply it by the reciprocal of the denominator. I'm going to skip this step when we do example 2 and 3, and I'm going to just go straight to here. So using the ratio test, okay, so you're going to take your series and you're going to write it as a ratio. All right, write it as a ratio, a sub n plus 1 over a sub n. Well, because we have fraction form here, you take a sub n plus 1 and multiply it by the reciprocal of a sub n, we'll do the same thing. What do we have here? So we have 5x, okay, to the n, and we have 5x to the first power, okay, for this numerator. This denominator here, 2n plus 2 factorial. So 2n plus 2 factorial, but instead of putting the factorial sign, because I can see what I need here, I'm going to call it 2n plus 1 and then 2n factorial. I'm expanding my factorial for this, okay? And then I'm going to multiply by this reciprocal, so I'm going to have 2n factorial in the numerator, and I'm going to have 5x raised to the n power in the denominator. So, so I took my numerator, and I'm multiplying it by the reciprocal of the denominator. So you can see the denominator, I just kind of flipped the denominator. But what did I do over here? Breaking this up, okay? Because as I'm writing this left side down, this left fraction, I'm eyeballing that right side to see what I need to make things drop out, okay? So 5x to the n, 5x to the first, well, keep the base to add the exponents, that's 5x to the n plus 1. Here I have 2n plus 2 factorial. Well, what is 2n plus 2 factorial? It's 2n plus 2 times 2n plus 1 times 2n factorial, okay? So once you have everything all expanded out, what can we do here? Well, we can cancel the 5x to the n's. They cancel, see? These guys cancel. This is what you want to do, is completely simplify my 2n factorials. What's one thing that's nice about the ratio test is it usually cancels out your factorials, okay? So we cancel this completely. Let's see what we've got here. We've got the limit is n goes to infinity, all right? So limit is n goes to infinity. What do I have left over in the numerator? I have 5x. What's in the denominator? I have 2n plus 2, all right? And I have 2n plus 1. So 2n plus 1. So this is what I have left over when I factor completely and factor everything out. Okay, value sign in here. So now let's go ahead and take the limit of the ends. We'll carry the x with us, limit of the ends. Okay, we don't have any ends in the numerator, so as the ends in the denominator get infinitely large, this fraction is definitely going to 0. I have 0 times the absolute value of 5x. This is what I have. Okay, 0 times anything is 0. Okay, and 0 is less than 1. Remember the conditions of your ratio test. You're going to use a ratio test, limit n goes to infinity, and you're going to take absolute value of the ratio of a sub n plus 1 over a sub n. And if your value comes out less than 1, okay, this comes out to be 0 for all values of x. If this comes out to be less than 1 for all values of x, okay, then it's a convergent. This converges. Ratio test. All right, so this is convergent series, which means our radius of convergence for this problem right here is going to be infinity. All right, it's a convergent series, so this converges for all values of x. 0 times 5x, absolute value of 5x is 0. Okay, and so this is going to be less than 1 for all values of x, which means you have infinite radius of convergence. All right, so here's how radius of convergence works for this example. All right, let's take a look at example number 2. We are going to use the ratio test. Example number 2, let's use the ratio test and see what happens with our power series using the ratio test. So I'm going to take the n plus 1th term and multiply it by the reciprocal of the nth term, okay? So the n plus 1 term, so what do I have here? So I'm going to have 2 and then change that to n plus 1, okay? And then that's factorial, so and then to x to the n plus 1 over, and then I have n plus 1 factorial. Change the 3 n's to n plus 1. I'm going to multiply that by the reciprocal, so n factorial in the numerator over 2n factorial x to the n. Okay, so I'm using my ratio test. I'm taking my a sub n plus 1th term and I'm multiplying it by the reciprocal of the a sub n term. I'm just going to go to that step, so I skip the complex fraction step. Now what do I want to do? Let me pull this apart and simplify what I have, the n plus 1th, and I want to pull this apart, simplify. All right, while I'm simplifying, I'm looking over here what I need to cancel. So I'm going to use some strategy here. 2n plus 2, 2n plus 2 factorial, but instead of writing factorial, I'm going to want to cancel the 2n factorial. So let me expand this. 2n plus 2, take 1 away, right? 2n plus 1, what does factorial mean times 2n factorial? Here's this piece expanded. What do I need here? I need that broken apart, x to the n times x to the first, right? Keep the base and add the exponents, so I need to pull this apart. N plus 1 factorial, let's call this n plus 1 times n factorial. And then that's multiplied by n factorial over 2n, that factorial x to the n. And so we're here. All right, so you can see the strategy that I used to pull these pieces apart, because my 2n factorials cancel, my x to the n's cancel, okay? What else we got? N factorials cancel, okay? So all these pieces go away. What do we have left over? So we've got the limit, okay, our n to infinity. We have in the numerator 2n plus 2, and we have 2n plus 1. And we have x to the first power. In the denominator, we have n plus 1, and that looks like that's it, okay? Now, take the limit as n goes to infinity. Well, let's see, we have more n's in the numerator than the denominator, so this is going off to infinity. This is getting infinitely large times our absolute value of x. So this is going to be infinity, okay? What is that? What is our ratio test telling us? Well, ratio test, when your value comes out to be greater than 1, it's diverges. This diverges for all values of x, which means our radius of convergence is going to be 0. This series here only converges at its center and no place else. The radius of convergence here would be 0. All right, so you see how this works? All right, so far, so we've got one more. All right, so here's an example like this is your condition 1 over there. So if your ratio test value comes out to be greater than 1, diverges for the ratio test. Comes out to be less than 1, convergence, all right? Because you have 0 here, 0 times any value is 0, so no matter what x is, there's a convergent series for number 1. Radius of convergence is infinity, okay? Example number 2, because you have infinity times x, that's infinity, doesn't matter what x is, You're going to have infinitely large greater than 1 every single time. So ratio test, when your limit comes out to be greater than 1, using the ratio test, it's a divergent series for ratio test because this is diverging, then your radius of convergence is 0. Let's see what happens with example number 3. So example number 3, here we go. Let's use our ratio test one more time. So we take the limit as n goes to infinity, absolute value, a sub n plus 1. So you have, what do we have here? We have x minus 1 to the n plus 1 plus 1 over, this is going to be n plus 1 plus 1, 4 to the n plus 1 plus 1. So I want to take all of these 3 n's and change them to n plus 1. So it's a sub n plus 1 over a sub n. So n plus 1, okay, and it's 4 to the n plus 1. Don't need a grouping symbol there. 4 to the n plus 1. All this goes over x minus 1 to the n plus 1. Okay? So your ratio test, you take the limit as n goes to infinity, absolute value a sub n plus 1 over a sub n. And because the a sub n plus 1 over a sub n for all these examples generates that complex fraction, I skip to the second step where I'm taking the a sub n plus 1 and I'm multiplying it by the reciprocal of the a sub n. Okay? All right, now I want to, let's simplify over here. Okay, so how am I going to put these terms together? All right, there's a strategy to it, right? I'm looking over here. Okay, so what do I need over here? I want x minus 1 to the n plus 1 to cancel. Well, I have n plus 1 here. So x minus 1 to the n plus 1, and then I have an x minus 1 to the first. Okay, so I'm going to separate those like this, okay? N plus 2, that's not going anywhere with me, so I'm going to call it n plus 2, and then what do I need here? 4 to the n plus 1 times 4 to the first, okay? So here's how I'm splitting these up, all right? X minus 1, keep the base, add the exponents, bring back here. The 4's keep the base, add the exponents, and so on. And why did I split it up like that? Because remember, I have that other eyeball looking over here as to what I need to cancel. So there's a strategy there. I have the 4 to the n plus 1, and I have x minus 1 to the n plus 1. All right, let's go ahead and simplify. What can we cancel here? We can cancel out the x minus 1's to the n plus 1's. Those cancel out completely, okay? So these are completely gone. 4 to the n plus 1, the 4 to the n plus 1's completely cancel out. I think that's all I can cancel here. So what do I have left over? I have the limit n to infinity. Okay, what do I have in the numerator? I have an n plus 1 and an x minus 1. What about the denominator? There's a 4 and there's an n plus 2. Okay, let's make sure we got all the pieces left over. Yeah. Now let's take the limit as the n's go to infinity. Okay, now the powers here are the same, so my coefficients, when I take the limit as the n's go to infinity, my limit for the n's, it's 1/4, but yeah, I've got the x minus 1. I still have this left over. All right, so now what do I do here? Well, you know, when the value comes out to be, you know, less than 1, converges, greater than 1 diverges. The first two examples, well, the first example came out to be 0. Okay, 0 times anything is 0, so converges for all values of x because it came out to be 0. The second example, well, that just came out to be infinity greater than 1. Okay, so that's just going to diverge for everything. You don't have a radius of conversion. Now, what about here, though? Okay, here it's not going to converge for all values of x because we don't have 0. But we do want to figure out what the radius of convergence is for this. So we want to take the 1/4 and the absolute value x minus 1. We're going to take this answer we got here, right? We wanted the interval of convergence, okay? We know the ratio test. When does a ratio test converge? Ratio test converges, okay? So converges when this quantity is less than 1. Okay, so ratio test converges when this quantity is less than 1. All right, multiply both sides by 4 so we can isolate our x minus 1, you know, the x with the center, so this is centered at 1. So multiply the left by 4, multiply the right by 4, and so here you have it. So for this problem right here, the radius of convergence, it's over here on the right hand side, your radius of convergence is 4 for this problem. Centered at x equals 1, this is centered at x equals 1, and the radius of convergence is a finite number 4. Okay, so and that's how your theorem works with the third case. Okay, so your ratio test. okay, you're going to use the ratio test to find the radius of convergence, all right? The value comes out less than 1, it's a convergent series. Value comes out greater than 1, it's a divergent series, okay? The first case is when you get 0 is with the first cases. When you use the ratio test, you use the ratio test and the limit comes out to be 0. The limit is 0, so converges for all values of x, all right? So if the ratio test comes out to be 0, then your radius of convergence is infinity. Okay, ratio test comes out to be 0, less than 1, it's a convergent series. Convergent series, you have infinite radius of convergence, right? Use your ratio test, and if you get infinity, okay, so really if you get infinity, all right, then what do we do for our ratio test when we get infinity here, okay? Greater than 1, okay? So anytime your ratio test comes out to be infinity, which is greater than 1, that means it's a divergent series for the ratio test. The ratio test diverges. You don't have a radius of convergence. Radius of convergence would be 0, okay? All right, so it looks weird to some people because the ratio test comes out to be 0, the radius of convergence is infinity. The ratio test comes out to be infinity, the radius is 0. It's because of the conditions of your ratio test, all right? So now what happens here? Well, when we get about 1/4 absolute x minus 1, okay, well we can't tell. So now how do we know when this kind of a power series is going to converge? Well, it's going to converge for some values of x and it's not going to converge for some values of x. So generate the radius of convergence here. So we're going to set this quantity here less than 1 because we're using the ratio test and we know this converges when that quantity is less than 1. So and you need to move the 1/4 to the other side, so this radius of convergence centered at 1 is going to be 4. Okay? Whew. All right, that's radius of convergence. Okay, we use the ratio test, and so I hope this video helps. If it does, please consider subscribing. Thank you so much for watching. Take care. Bye-bye.